Hello, our topic for today is section 4.4, which is binomial formula. What is this? It's a very simple section that actually where we cover the formula that's kind of important for algebra, and some instances of this formula you probably already know. For example, you all know that a plus b squared equals a squared plus 2ab plus b squared. That's basic algebra, you can FOIL it easily. You also know that a plus b cubed, maybe not completely by heart, but basically here is how it goes: a cubed plus 3a squared b plus 3ab squared and plus b cubed. Some of you know that one. But actually there is a formula that tells us how to expand a plus b to the n for any power n. And that's what our binomial theorem is, or binomial formula. So that would be theorem for .4.1. It says the following: if a and b are real numbers and n is an integer, then we have the following: a plus b to the n, like here for any n, equals sum when k goes from 0 to I. Okay, doesn't matter. That's how it is in the notes. And choose I, a to the n minus I, b to the n. Okay. Basically, if this closed form in the sigma notation still confuses you, although we discussed that in chapter 3, what this means is the following. You have n plus 1 members starting from 0, ending in an n, and here what they are. A gets the full power, and then A loses power one by one and gives them to B. So always the sum is n minus 1b, then n minus 2b squared, and so on, until toward the end b gets almost all the power. So let's say a squared b to the n minus 2 plus ab to the n minus 1 and plus b to the n. But then there are coefficients, and those are actually our coefficients are coefficients that we saw in section 4.3, where we counted combinations, and they are, here you go, n choose 1, n choose I, for I equals 2, n choose 2. This one is n choose n minus 2, although it's the same as n choose 2, and then n choose n minus 1. Let's squeeze it in. And finally n choose n, which is b to the n. So that's the meaning of this formula. So generally we have the sum of the powers where those coefficients are kind of A is losing power, B is getting power, and then binomial coefficients show up. I will write a proof because that proof is important, but to warm up for the whole story, let's see how it all works, for example, for these lower powers. So just illustration first, not proof. So let's illustrate this. So we saw how a plus b to the cube looks like, and then a plus b to the fourth. We can use it for that one. But actually, you see that here we need to calculate tons of these binomial coefficients. And one way to get all these binomial coefficients is to use Pascal triangle. And how does that work? So Pascal triangle. The way to build the Pascal triangle is the following one. You start with the triangle of ones. And then whenever you have two numbers, in the middle you write their sum, so that would be 2. And on the sides, in the beginning and at the end, you always get 1. Then again, on the next row, so this is like row n equals 2, this is row n equals 1, this is row n equals 0. For n equals 3, what do we get? 1 and 2 gives me 3, 2 and 1 gives me 3, and I have 1s in the beginning and at the end. And what's interesting, if you look at these numbers, these are exactly coefficients that we used here. 1, 2, and 1. Here they are, 1, 2, and 1 when I raise to the square. When I raise to the cube, my coefficients are 1, 3, 3, 1. Here they are 1, 3, 3, 1. So for example, if I need fourth power, I don't need to calculate all these combinations. It's actually, I'll put a 1 in front. Here I add 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4, and then 1 at the end. So if I know this, then I can immediately say, all right, so a plus b to the fourth equals a to the fourth plus 4a cubed b plus 6a squared b squared. It's the same formula as there, but instead of calculating those choose coefficients, these are called chooses, but people also call them binomial coefficients because they are used for binomial. Plus, next one is 4 again, 4ab cubed plus b to the 4. And then if you want to use it for fifth power, for sixth power, you can very quickly get these numbers. By the way, when we look at these binomial coefficients, then here is the reason why this is valid. For example, look what happened here. How did I get this 4? I added 1 and 3 and I got 4. What are those? This 1 is actually 3 chooses 0. What is this 3? Is 3 choose 1. When you add them up according to the Pascal identity from last time, I will get 4 choose 1 when I add them up. And that's exactly what you get below. So actually the fact that we add up two numbers in one line and get the number between them on the next line is exactly Pascal identity. So that justifies this. By the way, when we provide a proof, and that proof will be proved by induction, you will see how we will call Pascal identity. Alright, so what do we do so far? We have the theorem clearly stated, we illustrated a little bit, we connected it with Pascal triangle, now we'll go for the proof. Proof is a good exercise in proof by induction. So we will go proof by induction. Proof. Induction on n. On n, let's say greater or equal to 1. So first, for n equals 1. So what do we need to prove? That a plus b to the first equals, how do the member looks like? First one is a to the 1. And then last one is b to the 1. Generally that's what it is. How the right side looks like when n is 1, because this one chooses 1, this member and this member are the same. We only have 2 members. So that's true. And now what? Assume true for k. And then in my notes, I wrote it in sigma notation. Let me here on the board do it in this open notation. It might be cleaner for some of you. So, so for example, if I ask for that proof on the exam, you choose whichever one you like more. So you better have the alternative. So assume true for k. So what would that say? That a plus b to the k equals a to the k plus k choose 1, a to the k minus 1b plus k choose 2, a to the k minus 2b squared, plus k choose k minus 2 b to the k minus 2. It's long. Writing k choose k minus 1. Here I have more space, so I'm writing it a little neater. Plus b to the k. So this is inductive hypothesis that so for certain k greater than or equal to 1, we already established this. I put it in green because we can use this if we need it. So now I need to prove true for n equals k plus 1. Let me try to squeeze it in so that we have everything on the board. So here it is, left side. On the level k plus 1 is a plus b to the k plus 1. And I need to show that it's equal to this complicated expression. So what do? I want to connect it with inductive hypothesis. So I will write it as a plus b to the k times a plus b to the first, because that's basic algebra. Now what? Of course, this is my green guy. So I can replace it with all this that I have. Lots of writing, but it's okay. A to the k plus k choose 1, a to the k minus 1b, plus I'm just copying this. Maybe I don't need all these members, but it's safer to have it change gradually. Here it is. Brackets times a plus b. So what do here? I have a long sum, and that sum multiplies a plus b. So I want to do distributive law, so I will multiply each of them first with a, and then I will multiply it by b. So here it is, there will be a long sum. So here it is what I'll do. Let me write the first one in blue, and then second one maybe in black. So blue one with a. So when I multiply them with a, I'll get the blue version. So what will that do? Multiplying by a raises your power of a members. It will be like this. A to the k plus 1 plus k choose 1 and a to the kb. Because it was k minus 1 with that extra a is a to the kb. Plus k choose 2 a to the k minus 1b squared, da da da. So everybody gets an extra a. A cube b to the k minus 2 plus k minus 1 a squared b to the k minus 1, and finally last one gets a b to the k. Now what? Now I also need members that are multiplied by b. I will put them in red. And then you will see how I will write them so that kind of I have alike members below each other. I will need this line. So here it is. When I multiply by b, that first member, a to the k, I'll get a to the kb. And I will write it here. Only one, but that one I will write as k choose 0, because you remember last time any number choose 0 is plus. Then now this guy, he doesn't get extra a, he gets extra b. But look how nicely they are lined up. They are the same members, just with a different coefficient. And then here, on k minus 3 that's hidden here, I'll get extra b. So I will have, what would that be, k minus 3. A cube b to the k minus 2 plus. Now this guy with the b will be kk minus 2. A squared b to the k minus 1. Because this k minus 2 and 1 is k minus 1. Plus k choose k minus 1. AB to the k, oops, I went too far. A b to the k, and finally b to the k plus 1. We're almost done. Looks very unpleasant and complicated, but actually here is what will happen. I'll try to squeeze it in here. I don't know if I can, I'll try to see it here. What would that be? This is a to the k plus 1. Plus. These two are alike, so I'll factor out common factor. It's k choose 1 plus k choose 0, a to the kb. Those two together. Plus k choose 2 plus k choose 1, a to the k minus 1 b squared plus k minus 2 plus k minus 3 a cube b to the k minus 2 plus, now these two, k to the k minus 1 plus k to the k minus 2 a squared b to the k minus 1, almost there, plus this guy has nothing, but I can write it as what? K choose k, because that's 1. So k choose k plus k choose k minus 1 ab to the k, and plus this guy has only 1, I'll write it as what? K plus 1 choose k plus 1 b to the k plus 1. And now comes that crucial part, that basically what? Using Pascal identity, these two guys are two consecutive members, so that's equal. Next member, k plus 1 choose 1. So here it is, I have to continue here because this board is fairly small. Equals. I write this a k plus 1 on its own, and I write k plus 1 choose 0, which is 1, so you will see in a moment why. Plus these two together are k plus 1 choose 1, a to the kb. Those two together are k plus 1 choose 2, a to the k minus 1 b squared. Then these two together are k plus 1 choose k minus 2, a cube b to the k minus 2. Those two together are k plus 1 times k minus 1 a squared b to the k minus 1 plus these two are k plus these two are k plus 1 choose k, the higher one, a b to the k plus k plus 1 choose k plus 1, just b to the k plus 1. So the crucial thing was Pascal identity all the time. All these sums we were able to write as a single binomial coefficient. And what is this? This is exactly our right side. Our right side where n was replaced by k plus 1. K plus 1 choose 0. If you need it, that's 1. Then k plus 1 choose 1, k plus 1 choose 2, k plus 1 choose k minus 2, k plus 1 choose k minus 1, k plus 1 choose k, and then k plus 1. So generally formalized through. So this is the proof by induction. Since we prove true for 1, and whenever true for k plus 1, that is true for every n. So this is a very important formula for algebra and mathematics. If you need higher powers, then there is a way to get them automatically. And then just I want to do a couple of problems. That's it. The whole section is one formula, and I'd like to do a couple of problems so that you see how it all works in specific examples. So, example. Example 441. How do you use this formula to get 3a squared minus 5b squared to the fourth? So how can you use it? So basically, I just plugging in the expressions, but since formula is complicated, we want to make it sure that we know how to apply it correctly. So first, let me see coefficients. So you remember Pascal triangles: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Since I'm doing with 4 powered, these are coefficients that I need. So what would that be? So coefficients, let me write coefficients maybe 1, 4. This is always risky if you are not sure if you have enough space in between. But let's hope that we do. And then what do you do here? You take your first member, which is put it in parentheses, that's crucial, and take the full power on the first one. Then next one, you take cube power on the first one and first power on the second one. Here is the very important detail. Your formula works with a plus, and since I have minus here, I will actually think of this as plus negative 5b squared. So your second member includes a minus all the time. That's crucial. Plus 6 times, and then 3a squared goes to the squared, minus 5b squared also goes to the squared. Plus 4 times, I'll grade this one so that I have more space. 3a squared goes normally, minus 5b squared goes to the cube, and that one that I erased, you could just go negative 5b squared to the fourth. So this is the correct setup. So once again, crucial is that minus is always part of the second one in the parentheses. And then we have our binomial coefficients, and that's it. Now basic algebra, when you raise here, you erase both number and the power. So you get 81, a to the 8. Then what happens here? Plus 4 times 27, a to the 6 times negative 5b squared, if you want to be more careful. Plus 6 times 9, a to the 4th, 3 squared is 9, a squared squared, times 25, b to the 4th. Negative, when you square it, you get positive. Then it will be plus 4 times 3a squared times negative. When you cube negative, you get negative. 125 b to the 6. b squared to the cube is b to the 6. 5 to the cube is 125. And plus 5 to the 4th is 625 b to the 8. Here it is, we're almost done. Just basic algebra now. 81 a to the 8. What would that be? Minus 540. Because it's negative, 4 times 5 is 20. 540 a to the 6th b squared. How much is this? 6 times 25 is 150. 150 times 9 is 1350. So it's 1350 a to the 4th b to the 4th. Am I correct with this? 150 times 9, yes. And what would that be? This one is negative, so this is 1500, because 4 times 125 is 500, times 3 is 1500. A squared b to the 6 plus 625 b to the. Let me compare with my notes just in case I have everything correct. 81 minus 540 plus 1350 minus 50 plus 625. Perfect. All right, that was one example. What is the other one? Sometimes, especially if the power is fairly high, we just ask you to give us a specific member, not all of them. And see, here in this example, they say find the coefficient of the constant member. So I want constant member in the following development: 2x squared minus 3 over root x to the 20th. So here's the best way I would say to solve this problem. Actually, among all these members in these long sums, there's a formula for a generic member, and that formula says the following: tk plus 1, which is k plus first member, equals, and choose k, a to the n minus k, b to the k. In that sigma notation, this is k plus first member. K plus first. So what then? In this formula, I know some things, I don't know the others. I know n because my power is 20, but I don't know k. But here's what I'll do. I'll work with undisclosed k, so it will be 20. Choose k to be determined. This is my a. This is my b, but be careful, b includes the negative. So I can say on the side, so a is 2x squared, b is negative 3 over x. So it will be 2x squared to the 20 minus k, because n is 20, but k is undisclosed, and times negative 3 over root x to the k. So the question is, how much should I choose for k to make this constant term so that x has power 0? So I will combine these terms of working with undisclosed k in order to make a decision. This is the number, has no decision, an influence on my decision. 2 to the 20 minus k, and here is x squared to the 20 minus k. So I raise them both, times the negative 3 to the k, and here comes a little algebra. 1 over square root of x is basically x to the negative 1/2. So I'm raising it to the k, so that will be x to the negative half to the k. Here's my expression in a little abstract, undisclosed notion. So what can I do? I will erase this. I hope the explanation now stands. So what can we do? These are numbers, so it doesn't matter. This guy and this guy will both have x, so they will decide the power of x. So what would that be? Or maybe I can combine them. Say the following: 20, choose k, 2 to the 20 minus k, times negative 3 to the k. And here I multiply here for repeated powers. I have x to the 40 minus 2k times x to the negative 1/2 k. These guys have powers of x. And if I want x to the 0, then those two together, so this together gives me x to the 40 minus 2k minus 1/2 k. When you multiply powers, you add up the exponent. So if I want constant term, this has to be 0. And that resolves everything. So you will get what? 40 equals 5/2 k, because 2 and 1/2 is 5/2. If I solve for a k, I'll get 16 equals k. Here it is. So if we choose k to be 16, then x will have power 0. And then here's my answer. I'll say T17, because when k is 16, I get 17th member equals 20, choose 16, times 2 to the 4th, because k is 16 now. Negative 3 to the 16 is just 3 to the 16 because negative disappears on even power. And then here I can just check my work. X, oh, this is K, sorry, not X. Okay. That would be what? X to the what? 40 minus 32, which is 8, times X to the negative 8, and really they cancel out as we predicted, so here's our answer. So 17th member in this expansion will not have X, and it will be equal to this number here. And of course, on your exam, you can just leave this because 2216, which is 2224, which is the same thing. I just want to check the same. And then I somehow combine. Oh, I just found them misprinted in my notes. No, these two are not with the same power. I have to change that. All right, and then there are two other problems where it's not just calculation. We ask you to prove some identities, and one of them is very interesting. The other is also neat, but first one is particularly interesting. So how do you prove identities about numbers? So here it is, example 443. I ask this one quite often on exam, or variation of this one, so 443. Here's the property. If you add up the numbers from the same row in the Pascal triangle, you get 2 to the end. So what is this telling me? If you remember Pascal triangle, let's say if I add these numbers, what do I get? 1 and 4 is 5, and 6 is 11, and 4 is 15, and so sum is 16, which is 2 to the 4th. Here, when I add them up, 1 and 3, 4, and 4, 8, so I get 8, which is 2q. And that's what it says. It has to happen in every row Pascal triangle. When you add up all of them, you get powers of 2. And why is that proof? It's very simple. Why proof? Look at this. I will use the formula for 1 plus 1 to the n. How much is that? Is n choose 0, so this is my a, this is my b. They are both 1s, but I'll call the formula 1 to the n plus n choose 1 to the n minus 1 times b, which is 1, and so on. N choose n minus 1, 1 times 1 n minus 1, plus n choose n 1 to the n. And then what? 1 and 1 is 2, so on the left side I'll get 2 to the n. Who do I get on the right side? Since both a and b are 1, the only thing left are binomial coefficients. So I exactly get what we have there. Here it is. Very simple identity. Not only that, so we just proved it plugging in appropriate numbers in binomial formula, and sometimes I ask you, how much is 3 to the n? Then of course you would put 2 plus 1 and use something similar in the homework, or if you put 1 minus 1, you're going to get 0. So there are variations of that idea that appear on the exam. But I'd like combinatorially to mention also the meaning of this statement, because what it says is the following. I don't know if you remember from chapter 3, we said the following. How many subsets of power set of A has exactly 2 to the n elements if A has n elements? So if I take set of 5 elements, there are 32 subsets. On your quiz, there was one quiz when you had, I think, just 2 elements, and then you had 4 subsets. So what then? So this is the total count of subsets. So if I choose subsets, what can I choose? I can choose subsets that have no elements, which is just empty set, or those that have 1 element, or 2 elements, or n minus 1 elements, or all n. So this gives us total count. So this is the total count of all the subsets, and these are subsets according to the size. So these are those of size 0. This is size 1, size n-1, and this is size n. So if you are a subset, you must have one of these sizes, and then there's no overlap. So using a disjunction formula or union product principle and addition principle, then we have also this formula from combinatorial point of view. And then the other one that might be a little tricky would be, what is this one? So example 444. I'll ask you to simplify the following formula. Sum k goes 0 to n minus 1 to the k, and choose k 3 to the 2n minus 2k times 4 to the k. So for example, someone gives you huge expression like this and looks very complicated, but actually it's very easy to simplify it. Why? Because I would like this to look like this. So here's like comment in the programming. I'd like this to look like a sigma, like in my binomial formula, and choose k, a to the n minus k, b to the k, k goes 0 to n. This is binomial formula for a plus b to the n. So if I wanted this to be this, let's see. And k goes 0 to n, perfect. And choose k, perfect. Who is to the n minus k? An minus k looks here, and it looks here. So, what? And then who has k? Let me put that in different color. So b goes to the k. And here who has power k? This guy has power k. And this guy has power k. So in order to have this look like this, here's what I can do. I write it as sum. K goes 0 to n. I would then choose k as I should. And then what? I have a little trouble here. I don't want 2n minus 2k. I'd like n minus k. So here's the trick. You write it as 3 to the square to the n minus k. Because that's algebraically correct, because you multiply those and get this. Times, and then if I want the b, these two, I want them together under the same umbrella, negative 4 to the k. And now it's very easy. Now it really looks verbatim like this one. Who's my a? My a is 9. Who's my b? My b is negative 4. So according to Newton's binomial formula, this is just 9 minus 4 to the n, and this is 5 to the n. So generally things did not look completely like binomial formula, but after a few algebraic tricks, separation here and joining, separation on n minus k and joining on k gave me actually formula that looked exactly like the one I can call. And here is 5 to the n. So these are a couple of tricks. So this is useful practical formula. We need to understand how formula works to be able to apply it, to be able to calculate particular members or solve for index for which something is true, and then maybe prove some of the identities. Those are standard problems that show up in the exams.